the lecture notes for section 3 of chapter 5. In section 3, we're going to look at the types of simple machines. What is a simple machine? Well, a simple machine is a machine that does work with only one movement of the machine. There are 6 types of simple machines, and you can guess that that'll probably be a test question. A lever, a pulley, a wheel and axle, an inclined plane, a screw, and a wedge. And we'll take a look at all of these. And these are some of the machines that I want to see reflected in your Rube Goldberg devices when you get to that project. A lever. A lever is a bar that's free to pivot or turn around a fixed point. Fixed point the lever pivots on is called the fulcrum. The input arm of the lever is the distance from the fulcrum to the point where the input force is applied. The output arm is the distance from the fulcrum to the point where the output force is exerted by the lever. And again, we'll be doing some math problems related to the input-output force, mechanical advantage, and efficiency of levers. The output force produced by the lever depends on the lengths of the input arm and the output arm. If the output arm is longer than the input arm, the law of conservation of energy requires that the output force be less than the input force. If the output arm is shorter than the input arm, then the output force is greater than the input force. There are 3 classes of levers. The ideal mechanical advantage of a lever. The ideal mechanical advantage, or IMA, can be calculated for any machine by dividing the input distance by the output distance, and we saw that in the lecture notes from section 2. For a lever, the input distance is the length of the input arm, and the output distance is the length of the output arm. The ideal mechanical advantage of a lever can be calculated from this equation. Ideal mechanical advantage equals the length of the input arm in meters divided by the length of the output arm, also in meters. So again, ideal mechanical advantage, it's a number. Pulleys. A pulley is a grooved wheel with a rope, chain, or cable running along the groove. A fixed pulley, and this pulley, a fixed pulley, we'll show you the difference between the pulleys here in a second. This one, a fixed pulley is one that's like attached to something, attached to the ceiling, for example. A fixed pulley is a modified first-class lever. And I'm going to back up here a second and show you what a first-class lever is. I forgot to do that. A first-class lever come on, work. Well, I guess it doesn't want to work. Anyway, first class, second class, and third class. They're in order here. And we'll break those down like I say, when we get to some problems and when we do the reading in the book. So a pulley is a modified first-class lever. The axle of the pulley acts as the fulcrum. So just like if you envision here, and I can draw it for you, if we were to put an axis right through here, the fulcrum would be the wheel. A fulcrum, and a fulcrum is usually expressed as like a triangle, think of a seesaw. Here's the fulcrum, and input force. Here's your input force. You're pulling down on the rope here that says 4 newtons, and you're able to lift 4 newtons worth of weight, or apply a force of 4 newtons. Two sides of the pulley are the input and output arm. And again, input, output. A pulley can change the direction of the input force or increase input force, depending on whether the pulley is fixed or movable. Again, this is a fixed pulley. We'll take a look at movable pulleys in a minute. A fixed pulley is attached to something, like I said, that doesn't move, such as a ceiling or a wall. Because a fixed pulley changes only the direction of force, the IMA is 1. And I'm going to back up here a slide and look. IMA is 1. 4 newtons of force in, 4 newtons of force out. 4 divided by 4, 1. The ideal mechanical advantage is 1. A movable pulley is a pulley in which one end of the rope is fixed and the wheel is free to move. It's called a movable pulley. Unlike a fixed pulley, a movable pulley does multiply force. In this example, with a movable pulley, the pulley is free to move. The attached side of the rope supports half of the 4 newtons of weight. This is your output force, 4 newtons. The pulley, like it says, is supporting half of that, or 2 newtons. And by you pulling on the rope with 2 newtons of force, will lift that 4 newtons of weight. You have to apply a 2 newton force to lift the weight. The output force exerted on the weight is 4 newtons, and the applied input force is 2 newtons. So, like we said with a ramp, it makes the work easier. The output force exerted on the weight is 4 newtons, and applied force is 2. Therefore, the IMA of the movable pulley is 2. Oops. And we can do the math for you. IMA equals output force divided by input force. So the ideal mechanical advantage of a movable pulley in that example is 2. For a fixed pulley, the distance you pull the rope downward equals the distance the weight moves up. Kind of like we say a 1-to-1 relation. For a movable pulley, the distance you pull the rope up is twice the distance the weight moves up. A system of pulleys consisting of fixed and movable pulleys is called a block and tackle. And a little personal story from my life related to block and tackle. At the Lumberjack Special complex that I used to manage, there's a Lumberjack museum. And one of the displays in there is a block and tackle, and this one's made out of wood, and hopefully we'll be able to show you here a picture in a second. And we have it attached to a log that used to weigh about 100 pounds. Now, the log has dried out, so it probably weighs, over the years that he worked there, probably weighs about 80 pounds, but it's amazing. We have it hooked up to like a bull rope, and you can get a 4-year-old kid in there, and he can pick up that log using that block and tackle. The IMA of a pulley system is equal to the number of rope segments that support the weight. Here's an example, a picture of a block and tackle. This particular one has an ideal mechanical advantage of 4 because we have 4 segments. One, I use this here. We have one segment here. Oh, it won't work. Oh, come on. Does my marker work? One segment For some reason, my marker doesn't want to work on that graphic. One here, one here, one here, and one here. Okay, so you're seeing that you get 4 newtons of work by only putting 1 newton of work in. All right, let's see if this will play.
In a block and tackle system, the 4N weight is divided equally among each supporting rope. In this case, 4 ropes are used, so you have to use only a 1N force to lift the weight.
Next simple machine we're going to look at is a wheel and axle. A wheel and axle is a simple machine consisting of a shaft or axle, and in this example here, it's right here, the axle, like the barrel or the tube of the pencil sharpener. And this is attached to a larger wheel so that the wheel and axle rotate together. Here's the wheel. You turn the handle and the axle moves. Doorknobs, screwdrivers, faucet handles are examples of wheels and axles. Usually the input force is applied to the wheel and the output force is exerted by the axle. You know, when you think, well, how is a screwdriver a wheel and axle? You apply a force, you turn the handle, or you turn the wheel, which would be the handle, and the axle turns, tightening or loosening a screw. A wheel and axle is another modified lever. Wheel and axle, the center of the axle is the fulcrum. The input force is applied at the rim of the wheel. So like a pencil sharpener, how is that? A wheel and axle, what's the wheel and what's the axle? Again, the wheel is the crank or the handle, and the center of the axle is the fulcrum. The length of the input arm is the radius of the wheel. So like on a pencil sharpener, the length of that handle, that crank that you're using to turn the axle, that is the input arm. The output force is exerted at the rim of the axle. So for a pencil sharpener again, the output force is exerted at the tube that you put the pencil in. The length of the output arm is the radius of the axle. So the ideal mechanical advantage of a wheel and axle is given by this equation. It equals IMA, or ideal mechanical advantage, equals the radius of the wheel. And let's use the example of a screwdriver. The radius of the wheel would be the handle of the screwdriver. That's like the distance from the center of the wheel out to the of the handle out to the end, and divide that by the radius of the axle. So if you have like a Phillips screwdriver, it'd be the radius from the middle of that shaft, the screwdriver part, from the middle to the outer edge. A gear. A gear is a wheel and axle with the wheel having teeth around its rim. When 2 gears of different sizes are interlocked, they rotate at different rates. Each rotation of the larger gear causes a smaller gear to make more than one rotation. If the input force is applied to the larger gear, the output force exerted by the smaller gear is less than the input force. Gears also may change the direction of the force. When the larger gear is rotated clockwise, the smaller gear rotates counterclockwise. An inclined plane. A sloping surface, such as a ramp, that reduces the amount of force required to do work is an inclined plane. Mechanical advantage of an inclined plane. By pushing a box up an inclined plane, the input force is exerted over a longer distance compared to lifting the box straight up. The ideal mechanical advantage of an inclined plane can be calculated from this equation. Ideal mechanical advantage of an inclined plane equals the length of the slope divided by the height of the slope, or IMA equals L over H. And again, we'll be doing some problems later on in the week or next week related to these mechanical advantages, so you get an idea of how we use them and how to do them. The ideal mechanical advantage of an inclined plane for a given height is increased by making the plane longer. And again, like I said, we'll be doing some problems later so that more of this hopefully will make some sense. A screw. A screw is an inclined plane wrapped in a spiral around a cylindrical post. And what they're getting at here is this particular screw, all of these turns in the screw are inclined planes wrapped around this cylinder. You apply the input force by turning the screw. So you put a screwdriver in there, you turn it, that's your input force. The output force is exerted along the threads of the screw, so exerted along here. The ideal mechanical advantage of a screw is related to the spacing of the threads. The IMA is larger if the threads are closer together. However, if the ideal mechanical advantage is larger, more turns of the screw are needed to drive it into some material. A wedge. A door wedge. The wedge is also a simple machine where an inclined plane moves through an object or material. A wedge is an inclined plane with one or two sloping sides. It changes the direction of the input force. A doorstop is an example of a wedge that has one sloping side, but like a wedge that you would use to split a piece of wood, hit it with a maul, and a splitting wedge, that has two sloping sides. Compound machines. Two or more simple machines that operate together form a compound machine. When you get to the Rube Goldberg project and you're building your machines, they may be compound machines. You may apply, you may have a device that you use that has more than one simple machine in it, and that's fine for the operation. But in your explanation, if you're doing a video, for example, you need to explain that you understand the makeup of your compound machines. Where are the simple machines? A car is a compound machine. Burning fuel in the cylinders of the engine causes the pistons to move up and down. Your cell phones, the computer that you're using to watch this lecture, is a compound machine. A car, the up and down motion makes the crankshaft rotate, and the force exerted by the rotating crankshaft is transmitted to the wheels through other parts of the car, such as the transmission and the differential. Both of these parts contain gears that can change the rate at which the wheels rotate, the force exerted by the wheels, and even reverse the direction of rotation. And that will conclude the lecture for section 3 of chapter 5. Again, when you listen to the lecture, don't forget to go back into your My Big Campus account and complete the online review. Question 1 asks, what's the difference between a first class and a second class lever? The answer is the placement of the fulcrum. First class lever, first class, and a second class, it's the placement of the fulcrum. The fulcrum is this little thing. So a seesaw is a good example of a first class lever. Input force, output force. A second class lever, a classic example, is a wheelbarrow. You put a wheel here, you put your rocks or dirt in here, and here's you holding on to the handle of the wheelbarrow. So a wheelbarrow is a second class lever. Question 2, what's a third class lever? A baseball bat, a pulley, a screwdriver, or a wheelbarrow? Well, we know that a pulley is a modified first class. and a wheelbarrow is a second class, so we've got to decide between a baseball bat and a screwdriver. The answer is letter A. And go back and show you what choice A was. Choice A is a baseball bat. Oops. Output force exerted by a third class lever is less than the input force, but the distance over which the output force is applied is increased. Think about it. You are the fulcrum, your hands on the baseball bat. You provide an input force to the baseball when you hit it, and the output force isn't necessarily increased, but the distance over which your output force is applied is increased and the ball goes sailing. Question 3. A fixed pulley changes only the direction of the force. You pull down, weight goes up. And this concludes the lecture notes for Chapter 5. Make sure you go back and complete the online reviews associated with the different sections.